Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will be discussing about media access control. Let's start. As you can recall, if the link is point-to-point, the data link layer has only the data link control as the sublayer. However, if the link is broadcast, the sublayers are data link control and media access control. The media access control, or MAC, is responsible for resolving access to the shared link. Many protocols have been devised to handle access to shared link. It is categorized into three groups: random access protocol, the controlled access protocols, the channelization protocols. In random access or contention methods, no station is superior to another station, and none is assigned control over another. At each instance, a station that has data to send uses a procedure defined by the protocol make a decision on whether or not to send. This decision depends on the state of the medium. In other words, each station can transmit when it desires on the condition that it follows the predefined procedure, including testing the state of the medium. Two features gives this method its name. First, there is no scheduled time for a station to transmit. Transmission is random among the stations. That is why these methods are called random access. Second, no rules specify which station should send next. Stations compete with one another to access the medium. That is why these methods are also called contention methods. In a random access method, each station has the right to the medium without being controlled by another station. However, if more than one station tries to send, there is an access conflict called collision, and the frames will be either destroyed or modified. To avoid access conflict, or to resolve it when it happens, each station follows a procedure that answers the following questions. When can the station access the medium? What can the station do if the medium is busy? How can the station determine the success or failure of the transmission? What can the station do if there is an access conflict? Aloha, the earliest random access method, was developed at the University of Hawaii in the early 1970s. It was designed for radio LAN, but it can be used on any shared medium. It is obvious that there are potential collisions in this arrangement. The medium is shared between the stations. When a station sends data, another station may attempt to do so at the same time. The data from the two stations collide and becomes garbled. The original Aloha protocol is called pure Aloha. This is a simple but elegant protocol. The idea is that each station sends a frame whenever it has a frame to send. However, since there is only one channel to share, there is the possibility of collisions between frames from different stations. In this figure, there are four stations that contend with one another for access to the shared channel. The figure shows that each station sends two frames. There are a total of 8 frames on the shared medium. Some of these frames collide because multiple frames are in contention for the shared channel. The figure shows that only 2 frames survive, one frame from station 1 and one frame from station 3. Need to mention that even if one bit of a frame coexists on the channel with one bit from another frame, there is a collision and both will be destroyed. It is obvious that we need to resend these frames. The pure Aloha protocol relies on acknowledgments from the receiver. When a station sends a frame, it expects the receiver to send an acknowledgment. If the acknowledgement does not arrive after a timeout period, the station assumes that the frame has been destroyed and resends the frame. A collision involves 2 or more stations. If all the stations try to resend their frames after the timeout, the frames will collide again. Pure Aloha dictates that when the timeout period passes, each station waits a random amount of time before resending its frame. The randomness will help avoid more collisions. Call this time the back-off time, TB. Pure Aloha has a second method to prevent congesting the channel with retransmitted frames. After a maximum number of retransmission attempts, Kmax, a station must give up and try later. The timeout period is equal to the maximum possible round-trip propagation delay, which is twice the amount of time required to send a frame between the two most widely separated stations. The back-off time TB is a random value that normally depends on K, the number of attempted unsuccessful transmissions. A formula for TB depends on the implementation. One common formula is the binary exponential backoff. In this method, for each retransmission, multiplier r in the range of 0 to 2 raised to the k minus 1 is randomly chosen and multiplied by Tp, or the maximum propagation time, or TFR, the average time required to send out a frame, to find Tb. Note that in this procedure, the range of the random numbers increases after each collision. The value of Kmax is usually chosen as 15. Here is the flowchart for Pure Aloha, which became the template for the succeeding protocols. When a station has a frame to send, we initialize K, the number of transmission attempts, to 0, then send the frame. The station will wait for the timeout period. If the acknowledgement is received within the timeout period, the transmission is successful. If not, K will be incremented and check if it reached the maximum number of attempts, which is normally 15. If yes, the transmission will be aborted. If not, a random number r will be chosen. This random number r will be a multiplier for the backoff time. After the backoff time has expired, it will try again to send the frame. The process will go on until it has received an acknowledgement or it has reached the maximum number of retransmission. The vulnerable time, or the time that a possibility of a collision might occur, is 2 times the frame transmission time. Slotted Aloha was invented to improve the efficiency of Pure Aloha. It divides the time into slots of frame transmission time and forces the station to send only at the beginning of the time slot. The vulnerable time is the frame transmission time. To minimize the chance of collision and therefore increase the performance, the CSMA method was developed. The chance of collision can be reduced if a station senses the medium before trying to use it. Carrier sense multiple access requires that each station first listen to the medium before sending. In other words, CSMA is based on the principle sense before transmit or listen before talk. CSMA can reduce the possibility of collision, but it cannot eliminate it. The possibility of collision still exists because of propagation delay. When a station sends a frame, it still takes time for the first bit to reach every station and for every station to sense it. In other words, a station may sense the medium and find it idle, only because the first bit sent by another station has not yet been received. Here is a space and time model of a CSMA network. Stations are connected to a shared channel. At time t1, station B senses the medium and finds it idle, so it sends a frame. At time t2, station C senses the medium and finds it idle, because at this time, the first bits from station B have not reached station C. Station C also sends the frame. The two signals collide and both frames are destroyed. The vulnerable time for CSMA is the propagation time Tp. This is the time needed for a signal to propagate from one end of the medium to the other. When a station sends a frame and any other station tries to send a frame during this time, a collision will result. What should the station do if the channel is busy? What should the station do if the channel is idle? The persistence methods have been devised to answer these questions. First is the one persistent. The one persistent method is simple and straightforward. In this method, after the station finds the line idle, it sends its frame immediately. This method has the highest chance of collision because 2 or more stations may find the line idle and send their frames immediately. In the non-persistent method, a station that has a frame to send senses the line. If the line is idle, it sends immediately. If the line is not idle, it waits a random amount of time and then senses the line again. The non-persistent approach reduces the chance of collision because it's unlikely that 2 or more stations will wait the same amount of time and retry to send simultaneously. However, this method reduces the efficiency of the network because the medium remains idle when there may be stations with frames to send. The p-persistent method is used if the channel has time slots with a slot duration equal to or greater than the maximum propagation time. The P-persistent approach combines the advantages of the other two strategies. It reduces the chance of collision and improves efficiency. In this method, after the station finds the line idle, it follows these steps. 1. With probability P, the station sends its frame. 2. With probability 1 minus P, the station waits for the beginning of the next time slot and checks the line again. If the line is idle, it goes to step 1. If the line is busy, it acts as though a collision has occurred and uses the back-off procedure. The CSMA method does not specify the procedure following a collision. Carrier sends multiple access with collision detection augments the algorithm to handle the collision. In this method, a station monitors the medium after it sends a frame to see if the transmission was successful. If so, the station is finished. If, however, there is a collision, the frame is sent again. It is widely used for bus topology LANs. For CSMA/CD to work, we need a restriction on the frame size. Before sending the last bit of the frame, the sending station must detect a collision, if any, and abort the transmission. This is because the station, once the entire frame is sent, does not keep a copy of the frame and does not monitor the line for collision detection. Therefore, the frame transmission time T sub FR must be at least 2 times the maximum propagation time T sub P. To understand the reason, let us think about the worst case scenario. If the two stations involved in a collision are the maximum distance apart, the signal from the first takes time propagation time to reach the second, and the effect of the collision takes another propagation time to reach the first. So the requirement is that the first station must still be transmitting after 2 times the propagation time. To better understand CSMA/CD, let us look at the first bits transmitted by the two stations involved in the collision. Although each station continues to send bits in the frame until it detects the collision, we show what happens as the first bits collide. In the figure, stations A and C are involved in the collision. At time t sub 1, station A has executed its persistence procedure and starts sending the bits of its frame. At t sub 2, station C has not yet sent the first bit sent by station A. Station C executes its persistence procedure and starts sending the bits in its frame, which propagate both to the left and to the right. The collision occurs sometime after t sub 2. Station C detects a collision at time t sub 3, when it receives the first bit of A's frame. Station C immediately aborts transmission. Station A detects collision at time t sub 4, when it receives the first bit of C's frame. It also immediately aborts transmission. Looking at the figure, we see that A transmits for the duration t sub 4 minus t sub 1, C transmits for the duration t sub 3 minus t sub 2. Here is a more complete graph. Here is the flow diagram for CSMA/CD. It is similar to the Aloha protocol, but there are differences. The first difference is the addition of the persistence process. We need to sense the channel before we start sending the frame by using one of the persistence processes. The second difference is the frame transmission. In Aloha, we first transmit the entire frame and then wait for an acknowledgement. In CSMA/CD, transmission and collision detection are continuous processes. We do not send the entire frame and then look for a collision. The station transmits and receives continuously and simultaneously. We use a loop to show that transmission is a continuous process. We constantly monitor in order to detect one of the two conditions. Either transmission is finished or a collision is detected. Either event stops transmission. When we come out of the loop, if a collision has not been detected, it means that transmission is complete. The entire frame is transmitted. Otherwise, a collision has occurred. The third difference is the sending of a short jamming signal to make sure that all other stations become aware of the collision. We can say that the level of energy in a channel can have 3 values: 0, normal, and abnormal. At the 0 level, the channel is idle. At the normal level, a station has successfully captured the channel and is sending its frame. At the abnormal level, there is a collision and the level of energy is twice the normal level. A station that has a frame to send or is sending a frame needs to monitor the energy level to determine if the channel is idle, busy, or in collision mode. In wireless networks, a station needs to be able to receive while transmitting to detect collision. If the station receives its own signal, there is no collision. If the station receives its own signal and the signal is transmitted by a second station, there is a collision. In wireless networks, collisions must be avoided because it is difficult to detect. The carrier sends multiple access with collision avoidance was invented for wireless networks. Collisions are avoided through the use of CSMA/CA's three strategies: the interframe space, the contention window, and acknowledgements. The interframe space, or IFS, is a time period where it defers transmission even if the channel is idle. It can be used to define the priority of a station. For example, a station that is assigned a shorter IFS has a higher priority. The contention window is an amount of time divided into slots. A station that is ready to send chooses a random number of slots as its wait time. The number of slots in the window changes accordingly to the binary exponential backoff strategy. One interesting point about the contention window is that the station needs to sense the channel after each time slot. However, if the station finds the channel busy, it does not restart the process. It just stops the timer and restarts it when the channel is sensed as idle. This gives priority to the station with the longest waiting time. Acknowledgement guarantees receipt of frame. Here is a figure of the IFS and the contention window. Here is the flow diagram of the CSMA/CA. It is also similar with the Aloha protocol. The difference is the use of IFS and contention window. Thank you.